Hello guys, welcome again to this video. So in this video, as we have already told, we are going to evaluate gamma of half, or we are going to try to attempt it, and let's see how much we can cover in this video, because we also need to understand how the Euler reflection formula works, because that is essential. So let me just write out what we have found in the previous videos. So our results so far are as follows. So as you can see, gamma of n is n minus 1 factorial for all n natural numbers. This was the result we found in the first video. Then we had the recursive function for gamma, which is gamma of s is basically s minus 1 into gamma of s minus 1 for all gamma is greater than 1. Then we also found out the general integral, which is 0 to positive infinity e to the power minus ax x to the power n dx for any number n. So if it were a natural number, it would give you in terms of factorial, but since it is not, we just need to understand that this argument needs to be greater than 0, that is n needs to be greater than minus 1 for this gamma function to exist here, right? And then finally we also had another integral, which gave us that this is simply equals to n factorial for all n belongs to natural numbers, right? So we haven't yet discussed the part where we can use it for fractional values, but for that, as I told you, we would try to find out the value of gamma of half. So firstly, let me state to you the Euler reflection formula. This is basically the Euler's reflection formula, and it states that if you have a real number in the open interval 0, 1, then gamma of s multiplied by gamma of 1 minus s will give you pi by sine of pi s, which can be expressed in a elementary expression form, because pi is a constant which we know, and sine theta is something which we consider as an elementary function here. So what we do get is a value of gamma of s into gamma of 1 minus s in terms of our elementary functions. Now the proof of this is insanely hard, obviously, but still I'm going to let you understand how to do this proof and stuff. But for that, let us understand how this works. So firstly, the definitions. Firstly, putting s equals to 1 by 2, we get gamma of 1 by 2 into gamma of 1 by 2, because you see 1 by 2 and 1 minus 1 by 2 is also 1 by 2. This will give you pi by sine of pi by 2, right? Therefore gamma of half, since it's a positive quantity, would be root over of pi, since sine of pi by 2 is just 1. So this is the result we are talking about. And once we have this result, you will see it is easier to connect it to the more fractional values of gamma. So let us take a few examples, understanding how it works. So let's say we were to evaluate gamma of 5 by 2. Okay, so to evaluate this gamma of 5 by 2, what we can do is as follows. We can write this as, using the recursive property, we can write this as gamma of 5 by 2 minus 1 into gamma of 5 by 2 minus 1. So this here becomes 3 by 2 multiplied by gamma of 3 by 2. So see how we have used the property of recursion here, because we defined that this is valid for all is greater than 1, right? Therefore 3 by 2 multiplied by, now the gamma of 3 by 2 can again be evaluated in the same way. It can be written as 3 by 2 minus 1, as long as the argument is greater than 1 we can do that, into gamma of 3 by 2 minus 1. This would give you 3 by 2 into 1 by 2 into gamma of 1 by 2. Now since we do know the value of gamma 1 by 2, it becomes relatively simple, because it becomes 3 by 4 root pi, which is the answer, right? So as you can see, this gamma function is basically how we can find out all the different formations, and we can find out that all the half integer values can be evaluated exactly in terms of gamma of half. Let us take another example in terms of an integral now. Let us say you were given the integral 0 to positive infinity So as we know from our previous discussions, that this can be written as 0 to positive infinity e to the power minus 2x into x to the power 5 by 2 minus 1 dx, right? And if you see the integral that we evaluated right here, you see that it is equals to, when you have a power of x which is x to the power n, gamma of n plus 1 by a to the power n plus 1. So actually what we can do is we can use this representation directly, and we can write it as gamma of n plus 1 by a, here a is 2 to the power n plus 1. So what we get is gamma of 5 by 2 by 2 to the power 5 by 2. But we know the value of gamma 5 by 2, which is 3 by 4, and we have 2 to the power minus 5 by 2 into root pi. This becomes 3 by 4 means 2 square. This means 2 to the power 5 by 2 into root pi. What it becomes is 2 plus 5 by 2 is basically 9 by 2. So 3 by 2 to the power 9 by 2 root pi, and this is the answer for this integral. So having the value of gamma of half really lets you lose all your attention to different details, and it lets you evaluate all these integrals directly using some standard formulas. Of course, we have proved those standard formulas before, and if required, you may also have to prove some of the results when you are trying to use these formulas, at least for once in your answer sheet or wherever you're trying to do it, maybe in your publication, maybe somewhere else, but you need to prove it at least once, I think, because that is a good practice always, to use a formula that you're going to use repeatedly, to prove it at least once somewhere around. And this would actually give us the idea about how to evaluate these integrals. And finally, I would just give you a whisker of an idea of how to evaluate or prove the Euler reflection formula. So the formula was So it is 0 less than s less than 1. And what we can do is we can use double integration to evaluate this, right? So basically what we can do is as follows. We can write that gamma of s is basically 0 to infinity e to the power minus x to the power s minus 1 dx, and what we can write is gamma of 1 minus s is basically 0 to infinity e to the power minus let's say y, and y to the power 1 minus it's not it's basically 1 minus s minus 1 dy, or this can just be written as 0 to infinity e to the power minus y to the power minus s dy. And using these two different representations of the integral, we can transform this into we can multiply this and transform it into a double integral, and then we can evaluate it. So whatever that is, we will be covering that in the next few videos and how to get to the bottom of that. But for now, I think this should be enough for this video, so I'll see you in the next video. Thank you for watching. So please download the Breatter Maths app, which is given in the description. It is a mathematical app where you can find all the necessary statistical calculators like chi-square calculator, one variable means, population means, t-value, and much more. You can also find calculus related calculators like integration, derivatives. There is a section where you can find what's coming up next. There is a section completely devoted on mathematical notes where you can find notes on probability, statistics, calculus, and many more are there to come. In those notes, we have already explained all the examples, all the problems and theory, and we are just covering the video lessons and solutions of those here. You can check that out. Also, you can see the video solutions in a separate section where you can understand and give a feedback on what to expect next. You can ask for a problem, you can ask for a theory section as well. So please do check it out, and also do subscribe to Breatter Maths app and also its YouTube channel.